Carl, are you ready?
Yes.
Okay, let's start. Good morning, good afternoon, and good evening, my dear colleagues. So,
Carl, are you ready?
Oh, sorry.
Yes.
Okay, let's start. Good morning, good afternoon, and good evening. That's a live stream. So, okay, so welcome you again to this World River and Delta System Source to Sink webinar series. And today is 2021, number 32. That's really amazing. Now we have a 32 archived talk for this year. Last year we have 35. So now it's 67, number 67. So it's our great honor. We invite Professor Karl Stattegger. As you can see from Adam McKinney's University and Keele University, as we all know, he worked in Keele University for many years there, and come here talk about Parnaíba and São Francisco River Delta in Brazil, and to particularly talk about the natural and human impact. So before I introduce Karl, I want to mention this next week, next Wednesday and Friday, we have two talk from University of Washington, and is Hannah. She will talk about Irrawaddy River Delta, particularly focused on the tide river channel in the distributary and channel hydrodynamic. And Andrea, she will talk about its overview all the way from Amazon, from Yale River, from Mekong, from Papua New Guinea, from Irrawaddy, and she talked about sediment transport process from tidal river to off-shelf dispersal. But I want to remind you, because both of them located in California. So if we try to get them 9 a.m. as we always do, there will be 6 a.m. for them. A little bit brutal. It's a little bit too early. So I think it's the summertime now. So we do a little bit 1 hour delay. So next week, so we shift 1 hour later. There will be 7 a.m. for them. And so still earlier, but they graciously agreed to give a talk 7 a.m. and the US East Coast 10 a.m. London 3 p.m., Paris 4, Europe 4 p.m., Beijing will be 10 p.m. So that's exceptional for next week. Once again, the time is 1 hour delay next week. I will remind you by email. Oh, by the way, if anybody in the audience or on the YouTube channel, if you want to receive a weekly email about the future talks, please email me. I think you can find my email. And so next week, 1 hour different. Okay. Then Professor Karl Stattegger, as I mentioned, he has been in Keele University for many years. As you can see, he received his PhD from Austria, and then being an assistant professor there for 13 years, 14 years, and then moved to Berlin, Free University of Berlin, and then Keele University all the way, and until he retired since 2017, 3 years ago, become a full professor, in Poland at Mickiewicz University, Poznan, Poland. And I know Professor Karl many years ago in Shanghai when he visited Tongji, and we also have overlap working on the Mekong River Delta and many other delta, even the Gulf of Tonkin and the South China Sea, Sunda Shelf. As you can see, he's a very well-known professor, sedimentology professor. He studied the Africa, Madagascar, Asia, East Asia, South Asia, South America, as you can see, of course, the Baltic Sea in Europe. So today he will talk about South American, two very interesting river systems. So Karl, now you can share your screen for the presentation mode. Karl, you muted. Finally, no problem. Okay. Okay, please do a presentation mode.
Yes, yes.
Looks good. It looks good. Looks good.
Okay, so thank you, Paul. And in continuation of the lecture by Michel last Wednesday, I will bring you now to the northern part of Brazil. And before I start my talk, I will say thank you to the great teamwork I had with Elenice, Andre, Tiago, Fernando, and Caninde from the University of Natal in Rio Grande do Norte, especially for the work in the Parnaiba Delta. And I would also say thank you to Landim, to Junior, and to Adriani from University Federal of Bahia in Salvador for the work in the São Francisco Delta, where they did really a lot for, and especially Landim, for tens of years. And I should also mention this financial support we had for many years by Brazilian funding agencies like CAPES and CNPq, and also from the German Research Foundation. So I will give you a short introduction, then I will speak on the Parnaíba Delta, continue with the São Francisco Delta, and end up with some small conclusions. So on Wednesday, we were looking at that region in Argentina and also southern Brazil with Michel here. And now I will bring you to northeastern Brazil. And you remember probably the excellent talk by Jack Nitrauer in January on the Amazon Delta. And I will talk about the second and the third largest river systems in northeastern Brazil, the São Francisco and the Parnaíba Delta. If we look again at a general map here, then a curiosity is that in general, the shelf of the Brazilian coast is very narrow and very shallow. So the shelf break occurs already at 50, 60 meters or even shallower of water depths. And only in the north, if we are approaching the Amazon, the shelf is widening a little bit. But here you see the shelf is relatively very narrow. And so there's the discharge of the Parnaíba River and of the São Francisco River goes, for the most part, is transferred to the deeper parts of the ocean. On the other hand, we see also different influences. On the one hand, if we start from an artificial apex just at the northeastern corner of Brazil, then we see that towards the south, we have an increasing influence of waves, and to the west or northwest, we have an increasing influence of tides. So that means the Parnaíba Delta is a wave and tide dominated delta, and the São Francisco Delta is a wave dominated delta. And this you can also see in these classical approaches, this classical triangle of deltas, the Amazon, a tide dominated delta, the Parnaíba, a mixed tide, river dominated and wave dominated delta, and the São Francisco as one of the best examples of a wave-dominated delta here. Some hydrographic parameters just to show you the dimensions. And of course, this was mentioned several times, the Amazon River is by far the largest river in that region. The São Francisco and the Parnaíba River are much smaller, also compared to some of the Southeast Asian rivers, or compared to the Mississippi River, they are much smaller in water discharge and also in sediment discharge. And especially the São Francisco, you see there's almost no suspended sediment load leaving the river system. And we will discuss this later in some detail. If we look at the drainage basins of these two rivers, just based here on a relatively simple geological map of Brazil, then there are some differences. In the Parnaíba drainage basin, we have more or less only sedimentary rocks in this hinterland here, while in the São Francisco basin, we have also a lot of Precambrian and other crystalline rocks, especially in the middle and in the lower courses of the river here. Now let's go to the Parnaiba Delta. This Parnaiba Delta is in part a natural reserve, and there are several attempts to protect it. On the other hand, a lot of problems from the upstream river is coming now into action, and you have a highly variable land and seascape. So on the one hand, you see nice coastal dunes in front of wetlands, extensive mangrove forests. Here an example of a tidal channel mouse, and on the other hand, also some construction works on the outlet of one of these distributor of the main two distributaries. This is the smaller one, and you see clearly that you have here a lot of suspension load coming out the river. And this suspension load is generally driven, in this case, this would be the western direction. As you can also see from the turbidity, this is the prevalent coastal current system. I will come back to this a little bit later. If we look at the drainage basin again, which is shadowed here, then we see that in this river we have only one reservoir so far, this Boa Esperança reservoir, and this is supplying or is supplied by less than 25% of the drainage area. So there's a relative limited effect of this reservoir on the river system further downstream. But in the future, a severe problem may arise by the planning of some reservoirs in the middle and in the lower course of the river. So if we look at the delta itself, we see here in the eastern part the main region of the present-day Parnaiba Delta. In the western part, we have a region of tidal channels, and we think this have been old distributaries in former times. And at the coast, we have a lot of nice beaches and coastal dune fields all along this delta system. And in green, you see also a line, what we assume the shoreline at the maximum Holocene transgression. There is only little evidence of a mid-Holocene sea level high stand. It was probably less than 1 meter above present mean sea level, but the shoreline was more or less here. And you see in this last 6,000 years, the delta prograded by 10, 15 kilometers. What else can we see? We see that we have a northwest to west directed coastal current system here. We have a trade wind system which prevails continuously over the year, northeasterly winds with an average velocity of 2 to 6 meters per second, sometimes a little bit stronger, but normally we have no storms in that region. From the winds, we have a significant wave height of 1 meter roundabout. And we have a tidal amplitude of 1.7 to 3.3 meters, which drives these tidal currents here in these tidal channels. And finally, of course, we have the river outflow, and actually we have 3 river mouths, one the main Parnaíba River, and a smaller one here in the east, the Iguaraçu river mouth. If we look at the shelf in front of this delta, to the bathymetry. It's the situation, as I told you at the beginning, we have a relatively shallow continental shelf, which is not very wide. You see the shelf break occurs here between 50 and 60 kilometers distance from the coast, a relatively sharp break, and this shelf break occurs in relatively shallow waters. We have water depths of around about 40 meters here. This is a three-dimensional picture here, a sharp shelf break and a relatively steep gradient of this continental margin here down to the deep sea basin. And if we are going closer to the shore, you see here the shallower part of the shelf, and we have also some morphological depressions here indicating the former course of this Parnaíba River during the last sea level low stand. We did some seismic survey there, and we could follow this river valley, the main river valley, in the seismic survey. So this is the interpretation that we had really a relatively wide river system, which not very wide in comparison, of course, to the Amazon or to the large East Asian rivers, but more or less of the same magnitude as this river has today. And in addition, we have also in the western part, in the continuation of the present-day tidal channels, these incised valleys, which are narrower and sometimes a little bit deeper incised here, but also here good evidence that some of the river branches were active also during the last sea level low stand, and the river system incised onto the shelf, onto the shallow shelf, and then went further on to the continental slope and to the deeper part, of course. We took several Vibrocores, these samples, and these Vibrocores were not very long, but what we can make out is a clear zonation in these mangroves. So on the one hand, the oldest here, the first mangrove phase, is close to this former coastline. This is, again, you can see it, I think, very clear, what I showed you before in this, with this green line. And here the onset of the first mangrove phase goes back to around about 7,400 years before present. So this is all calibrated years, of course. So that means we are following the general regulation that the onset of these modern deltas started around about 8,000 years before present, or maybe a little bit later. Then we have a second phase of these mangroves, which are dated between 5,000 and 3,000 years before present, more or less, in this zone here. And then we have a third zone of very young mangroves here, and also here and here. And these mangroves are younger than 1,500 years. But since we have no deeper cores, deeper drill cores available at the moment, we have no good idea of the general and the larger architecture of this delta, but principally we can see the evolution during this last 7,500 years, more or less. So for the coming back to this specific situation we have today, and we think that this present day tidal channels, which are more isolated, more or less, have been connected in former times to the Parnaíba river system, and the changes occurred by some kind of delta switching triggered by neotectonic eastward tilting. So we have some evidence for neotectonic movements in that region, which did also occur during the last 1,000 years. There's also some small seismicity available, some evidence for this. And if you look at this here, this area here is the only present-day connection from the main Parnaíba river system to this tidal channel system. And this was also almost abandoned around the year 1950. But the local people, they worked on this channel and they widened and deepened it a little bit so that it can be used as a local waterway connecting the Parnaíba Valley to these tidal channel regions further to the west. So on the one hand, this eastward tilting, and comparing to that what I told you just before, we have a first phase of this delta outbuilding and the formation of a wave and tide influenced asymmetric delta, and with this relatively strong asymmetry due to this alongshore coastal current system, which is directed to the west or northwest. And then a flipping back to this situation here again. And now we see that we have really an upstream orientation, upstream to this alongshore current system of this Parnaíba river mouth system. There's also some other evidence. Of course, this is not completely reliable, but if you look at old maps, old topographic maps, for instance, here from a geographic atlas published by Mr. Heck in the year 1842, then you see also that you have this western connection to the Parnaíba River. And there are several maps available. There's another example, a map of, I don't know the real source of this, but it was republished in the year 1902. And it shows you also that you have on the one hand, this present day main Parnaíba River, but also a real good connection to this western part. So that means that this was abandoned probably only during the last centuries, but we have no real proof for this. If you look at the actual river mouth, then we see that we have a strong progradation of this part here. You see here the scale, and just during the last 40 years, when satellite images were available, we could see a progradation here of almost 3 kilometers in that direction here. And we can also see that the sediment accumulation in this part increased, especially during the last years. During the last 2 decades, we have much larger growth rates than before. The general idea of this updrift migration of a river mouth is in response to some increase in the river discharge. This could be a seasonal increase, but could also be an increase for some longer period of time. And first you have accumulation here of sediment. And then if you have this oblique wave approach, you have this flow differentiation, and some parts are directed towards the river mouth again. And then finally, you have the formation of such a boomerang-shaped spit system. And this is exactly what we can observe in very recent times, or let's say for this last 40 years, where we have this satellite data available. If we look at the sediment, suspended sediment concentration, then I will show you just 2 pictures here for the complete area of this Parnaíba Delta. On the one hand, the situation during the ebb phase here, you see the maximum concentration. So this is on the one hand proven by samples, by sediment samples, and on the other hand, the examination of or the elaboration from satellite images again. And here you see on the one hand this river plume here, and also a lot of suspended material here in this tidal channel system, which is fed, at least in part, from this river plume here. So this is the situation during the ebb phase. And this is the situation during the flood phase, when in the river, some part of the sediments are pressed back, and also we see a relatively strong inflow in these tidal channels to the inner parts. But this holds only for the wet season when we have a high river discharge. If we look at other periods, and here you see a pattern of precipitation and suspended sediment concentration for this river mouth system, we have a very clear seasonality. Most of the precipitation we have in the first half of the year, and then we have a decrease to almost zero in the second half of the year. And if we are in the phase of relatively or shortly after the maximum precipitation, then it's the picture as I showed you before for the ebb phase, that we have a very significant river plume, which is coming out the main river channel here. In the dry season, the situation looks different. We have also here indication of this river plume, but the concentration is much less. And also during the flood phase, we see that a little bit of sediment is pushed back, but more of the sediment is distributed again along shore and is further distributed generally to the west with this longshore current system. So this is what we learned from the satellite images and the suspended sediment concentration. We used satellite images also in reconstructing changes of the shoreline. And what I'm showing you here is the gross shoreline changes between 1984 and 2017, again from Landsat satellite images. And you see here the areas in green, they are showing general sediment accumulation here. And the areas in red show the sediment erosion and the shoreline retrogradation. We don't see a very clear picture, but we can see that, especially here in the surroundings of the river mouth, on the one hand, on the spit system, which is a special case and what I just showed you before, and also on the eastern side of this river mouth, we see a relatively high sediment accumulation and the growth of the shoreline, a progradation of the shoreline up to 30 meters per year. A similar situation, but with weaker rates, we see on the second distributary here, the Iguarazu River, but here the values are some not exceeding 4 or 5 meters per year in average. So this is the long-term situation, and we see strong accumulation close to the river mouth and some erosion here, especially in the western part. So that means the sediment is brought in that region only by the longshore current system, and since we don't have a direct connection except this small artificial channel here to the real Parnaiba River, we have no sediment supply, no riverine sediment supply from the land side here. And therefore, we have these erosional effects here. We did these investigations, of course, also on shorter time scales. And you see several sectors having accumulation, other sectors show relatively strong erosion. But I will bring your attention to 4 special scenarios. Here, this period between 1995 and 1999, we have almost completely erosion in all the area. a similar situation in the period between 2009 and 2012. And on the other hand, strong sediment accumulation over major parts of the delta region in the periods between the year 2007 and 2009 and 2012 and 2014. To explain this, we have to go back to the rainfall and discharge data. And of course, if you look at the monthly data, again, the averages for this 33 years, we see a strong congruence between the monthly rainfall and the average monthly river discharge. Here, this is Lusilandia. This is the lowermost gauging station, and this is situated around about 200 kilometers upstream the river mouth. And you see a nice correlation here, but of course some delay with the discharge in comparison to the rainfall here. And if we look at the annual scale here, then we see also several changes and a dramatic decrease or increase in rainfall. And this is closely correlated to the ENSO Southern Oscillation with the negative effect, very dry years during an El Niño period in eastern Brazil and wet years during La Niña phases in this region. And this holds also for the average annual river discharge. And also here you see the weak discharge during El Niño phases and peaks in discharge during the La Niña phases. And comparing this, the multivariate ENSO index to this rainfall and fluvial discharge and to this coastal change rates in some on the annual scale, we can see for this specific intervals I showed you before that we have a strong El Niño period in this year and the negative response by the rainfall, the river discharge, and also by erosion on the coast. Then the next was in the temporal succession, this La Niña period where we have high river discharge and also a lot of sediment accretion at the coast. Then again, an El Niño period, which is not so clear, but also shows a minimum, at least a local minimum here in the rainfall and discharge, and also a retreat in the shoreline configuration. And the last one, La Niña event here with positive values on the river discharge and also increasing values of sediment accretion here. So there seems to be a relatively good relation between small scale seasonal changes and also the temporal effects of the El Niño, La Niña changes on the scale of 2, 3, 4 years or so. So now I will give you a short summary for this Parnaíba River here. So the rainfall and river discharge drive the shoreline changes in the Parnaiba Delta with respect to seasonal changes and ENSO effects. A high turbidity zone extends from the river mouth plume of the main distributary to the western tidal channels. The turbid water enters the tidal channels during the flood phase and leaves during the ebb phase. Coastal accretion or stability characterizes the eastern active part of the delta, while moderate erosion prevails in the western abandoned part, damped by the westward directed longshore sediment transport from the Parnaíba river mouth. And this one larger reservoir, the Boa Esperança Reservoir, 700 kilometers upstream of the river mouth, which is supplied by less than 25% of the drainage basin, does not influence sedimentation in the delta significantly, at least from what we can see now. But the big question is, how will the damming along the lower course of the Parnaíba River influence the stability of the delta in the future? Okay, now let's go to the São Francisco Delta. Again, here the drainage basin, and what we can see here, that in difference to the Parnaíba, this drainage basin, here more than 98% of the drainage area affected by damming, and especially by large reservoirs in the middle and in the lower course of the river. And only these lowermost parts, the last 200 kilometers from the last reservoir to the shoreline, the river is in a natural state, a quasi-natural state again. And this makes the situation a very special one. On the other hand, the São Francisco is well known as a wave-dominated delta. You can find this as an example in many textbooks. The delta evolved during the last 8,000 years. And you see quite nicely here, for instance, the different the dune fields and the coastal ridges, the sand ridges, which developed from here initially down to the present day coastline. And we have a relatively good idea how this delta evolved during the last 8,000 years with the progradation of the fluvial deposits, and especially from these dune fields. We can, in the meantime, distinguish 6 different beach ridge series from old to young, and I will not go into very details for this, but I will focus more on the present day situation. So what we can see here is a very strong coastal erosion, which happened especially during the last decades. Starting this story, I start the story with just comparing an old map, one of the oldest available from 1853, to the situation of an aerial photographs in the year 1960. And you see there is not, of course, there are some changes. The riverbed is getting a little bit wider here, but principally the shoreline configuration did not change very much also here. So this was not investigated in the old map very properly, but the differences are only moderate. But then see, if we look at the last decades, we see we had one good reference point, and this is this lighthouse, which was situated 280 meters inland, this lighthouse here, before the last phase of the upstream river damming. So this is the situation for the year 1984. And then look, 14 years later, when the damming system was fully operating for several years already, this lighthouse is already at the shore. Again, if we move 6 years on, the lighthouse is 225 meters in the water. And if we move another 4 years, the lighthouse is 360 meters from the shoreline. And continuing this, or resuming again the situation for the year 2004, the distance 225 meters, in the year 2011, 400 meters, in the year 2014, 445 meters, and here you have also some accretion of sand, coastal sandbars, which go and appear and disappear in relatively short periods because the river is bringing out a lot, or not a lot, but at least still some sand. I will come back to this in a few minutes. And this is the situation for now, or for 2 months. the position of the former lighthouse, a completely different coastal configuration, and a minimum distance of 800 meters to the existing shoreline. So this is really a very strong and intense erosion which just happened into 3 decades. And the colleagues from Salvador also did the same what we did for the Parnaíba coast. They looked at the coastal accretion erosion patterns along the coast. And here you see the contrary to what I have shown you for the Parnaiba Delta. Here we see the most erosion at the river mouth system. And on the other hand, an accretion here, sediment accretion, because we have the downdrift movement of the sediment by the longshore current direction, which is directed from northeast to southwest. And so we have a relatively high, you can see this in this diagram here, here's the river mouth, here's the northeastern sector, where we have a relatively stable situation, but not much changes. Then here the strong erosional effect, the strong negative shoreline migration, and then in this portion again, in some parts a relatively high accretion, or at least a relatively stable situation. But the river mouth is really deteriorating rapidly. And this is due to these river dams here, which you can see on this map. On the one hand, a relatively large one here, the Sobradinho Reservoir, and here a series of several reservoirs, and the last, the Xingu Reservoir, I mentioned it already, this was finished in the year 1984. And if you look at this, you see that we have above the dam a water level of 130 meters above mean sea level, and below the dam we are at just 20 meters above mean sea level, and the river depth here is up to 10 meters already, because it's a relatively big river. Here's some data, this is not interested, but the storage capacity, as you can see here, is relatively large here in this system. And the problem is that most of these reservoirs are situated in the middle and the lower course of the São Francisco River, and therefore the river system cannot regenerate in the final part. On the other hand, of course, you have the effect of flow regulation. You see here the peaks of extremely high water discharge here before the damming was active, and then a much more regular flow during the last decades, and a tremendous decrease here during the last 3-4 years. This is probably also associated to a general decline of rainfall, 27% since the year 1960. So it means that this complete region here is getting drier, or at least parts of this region. And then Landim developed 4 phases or 4 intervals here of this river discharge, a medium discharge, a phase of high discharge in the late 40s of the last century, then again returning to normal conditions, then a high discharge phase between 1980 and 1986, and then again a relatively low discharge during the last decades here. And as you see here from the detailed data, it seems to be to decrease continuously. If you look at satellite pictures, you can see the same. So this is a picture, not a new one, but from February 2001, and you see there's no sediment coming out the river, at least no suspended sediment coming out the river. And also at the end of the wet season, you see that you have less sediment in the river than along the longshore, or the sediment coming along with the longshore transport from the coastal current here. But the river is, you could also say it's a negative river plume. So some data to this. actually, we see the upper limit of the saltwater intrusion here, reaching around about 10 kilometers upstream from the river mouth, and the upper limit of the tidal influence, but the tidal range, I didn't mention it, but I showed you in the first slide of the first picture of this São Francisco Delta, the tidal range, the tidal amplitudes are changing at less than 2 meters at maximum, and therefore also the upper limit of the tidal influence is limited to around about 30 kilometers. Now, and here some data on salinity and suspended matter. Here the situation close to high tide or after high tide, when we have this salt wedge moving up the river valley here, but you see it's limited. You have a little bit here, and sometimes it may come up to this region, but then after 10 kilometers, this will stop. And of course, on the other hand, if we are close to low tide, we have the more pronounced river outflow. And we have also a mixing zone here, and in the mixing zone, we have increased flocculation. L2, the suspended sediment content is extremely low. You see sometimes it's 1 milliliter or a little bit more than 8 milliliters per liter at maximum. So this is really not much. And the main sediment transport goes on by sand waves at the bottom. So we have bedload transport by subaqueous dunes. These dunes have dimensions of several tens of meters, and you see they can be up to 1.5 meters high. Sometimes you have simple dunes, sometimes you have smaller superimposed dunes. Here you have the side scan sonar pictures looking at the surface for this, and you see these are relatively large subaquatic dune bodies which are developing here. The grain size is medium sand with a mean size of 0.4 millimeters and the range from 0.14 to 0.9. And what we also could do is, or what we try to do is to calculate from the dimensions of the dune bodies and the velocities of the stream flow, the migration rate here at the situation around about 6.5 kilometers from the river mouth. And you see that the dune migration rates may reach in some periods of high discharge, some 20-25 centimeters per hour. And in most part, it's between 5 and 10 centimeters per hour. So that means a dune will move 2, 3, maybe 4 meters per day, not more. But this is possible only for this last 200 kilometers below the last reservoir. Here you see the relation to the river velocity and also the tidal oscillations, which are relatively small. So they are barely exceeding 1 meter here, and they never will exceed 1.8 meters, as I mentioned before. So, but this is not the complete story. So there's on the one hand, no sediment coming out the river. And on the other hand, there's a big project going on of diversion of the São Francisco River to the northeast for additional water supply of the dry northeastern hinterland. The plans are to use at maximum 62 cubic meters per second of the São Francisco discharge. Under normal conditions, this would be less than 3%, but since the discharge is going down and going down, this percentage will get higher, of course. And the first part of this river diversion was launched in the year 2017, this eastern connection here to the Rio Parnaíba, not Parnaíba, but Parnaíba. And here, the work is going on to the north, to the rivers in Rio Grande do Norte and Ceará, also very dry regions here in the hinterland. And the argument for constructing this is to guarantee the water safety for 10 million people in these states of Pernambuco, Ceará, Rio Grande do Norte, and Parnaíba. And especially during the last decades, these regions are suffering heavily from droughts. And the first part, as I just told you, of this diversion project was launched 3.5 years ago. Okay, so now short summary for the São Francisco Delta. We have very little fine-grained sediment in the river mouth. We have mainly bedload sand transport of sand by large subaquatic dunes and sandbars. It's a typical hungry river downstream the last reservoir. That means we have relatively strong river incision into and erosion of Precambrian crystalline and late Cretaceous tertiary sedimentary bedrocks. Therefore, we have this high amount of sand still coming out the river. And we have the recent sand accumulation from the lowermost river course in front of the river mouth. But it's only from the lower river course. Nothing comes down, or almost nothing, from the area which is dammed. And we have to expect a diminished discharge to the shore by the river diversion which is going on. And here the big question is, how long will the river take to erode the basement rocks downstream, the last, this Shingo Dam, so that a wave-dominated estuary will extend 200 kilometers upstream until this dam. Some engineers say this may last only 3-4 decades, but we don't know. And actually, in comparison what I mentioned before, the estuarine influence can be followed 30 kilometers upstream from the river mouth. So that's it. And instead of conclusions, I would like to refer to this nice paper of Jair Sivitsky and co-authors who identified 5 categories of deltas in order of increasing relative sea level rise and increasing flood risk. On the one hand, we have deltas none at risk. So we have aggradation rates unchanged and minimal anthropogenic subsidence and the outer upbuilding of the delta. And the Parnaíba River, we can take as an example for this. Then we have a category of deltas at risk, deltas at greater risk, deltas in peril, and finally deltas in greater peril. And this means no or very little aggradation and accelerated subsidence increase the rates of relative sea level rise and the shoreline retreat very strongly. And on the one hand, we can say the Parnaíba River is still in a quasi-natural state, but the planned damming in the lower course will bring it in direction to the São Francisco River and the strong erosional efforts at the shore, which we can observe there already now. And the last one is again here, the São Francisco River with more than 95% of sediment retention, and only this lower part here is supplying sediment to the shore. And on the other hand, less than 10% sediment retention in the Parnaíba River, but also the problem of some planned river damming projects here, which are at the moment in, I would say, in an initial state, but nobody knows what will happen in the future. And these rivers, of course, are not alone. And the very last one, the Mekong River, was discussed several times in this lecture series. And here we have also good scenarios for the future. And if we look at the Mekong River system with the definite future dams, we will have a sediment retention of 51%. And if we assume a full build-out scenario, which is also at least discussed, then we would have a similar situation like we have in the São Francisco Delta. But on the other hand, the Mekong Delta system is completely different, and the people in Vietnam will suffer much more from the upstream river damming than the people do in Brazil, but also here it's not that nice. And I thank you for your attention with this picture of this Parnaiba Delta. Thank you.
Hey, Karl, thank you very, very much for this so informative, fantastic talk. It is great. So let's say that if you have any question, please go ahead, unmute yourself. You can ask Karl directly. So Karl, given the size of these two rivers, so because they only deliver very small amount of sediment to the sea, and so any human impact will be very severe to the river mouth. As you mentioned, São Francisco already more than 90%, 75,
yeah, 95, yeah.
95% retention. So
yes.
Parnaíba is 10. But in the future, Parnaíba could be very soon, more than half or maybe 70, 80, 90% sediment trapped.
Yeah. Yeah.
There will be a disaster for the shoreline, wetland, lagoon area, the Delta region, right?
Yeah. This is a disaster, but you see, on the other hand, there are really conflicting interests because the hinterland of northeastern Brazil is very dry. Therefore, they initiated this river diversion from the São Francisco to bring more water to these dry regions.
Oh.
This is also an argument for damming the Parnaíba River.
Interesting.
And several other rivers.
Okay.
And so finally, this will be a political issue.
Actually, China had already had this kind of problem already.
Yeah.
And, for example, the Yellow River already very dry and very low water discharge, but this still take more water for human industry, agriculture purpose, make the things even worse.
Yeah, and therefore I showed you also this example of the Mekong River.
Yeah.
There's the similar situation.
Wow.
That especially the Chinese have huge damming plans.
Yeah, that's the other very hot issue. But anyway, we know the East Asia, more small river like Parnaíba or São Francisco already dried. So we paid attention to Yangtze Yellow, but actually many small river systems like a Rhine-He, like a small river, they are already. But anyway, so that's Jim Best, you have a question, please go ahead, Jim.
Yeah, thanks, Paul. Thanks, Karl. That was just a fascinating talk, actually. So I'm really interested, and as Paul said, lots of information. I really didn't know very much about these two systems, so thank you. It's really informative. I had a couple of questions related to Paul's question. For the São Francisco, are there any plans to retrofit any of the dams to aid sediment bypass? And the second question is sand mining also any issue in both of these river deltas and the channels?
No, not. There is a small sand mining going on in the Parnaíba River, but this is really only for the locals. The locals, and you cannot compare it what's going on, for instance, in the Mekong Delta.
Right. Yeah.
And so this situation is still stable. In the São Francisco, there is, so far I know, there's no sand mining at all.
Okay. And are there any, have there been any plans to do any retrofitting of the dams? Yeah.
Not so far I know, because you see, I showed a short table, but I didn't discuss it. Also, the time is short. But the first reservoirs were constructed in the 50s and in the 60s.
Yeah.
And the last ones in the 80s. And at that time, the technology was not so good as it is today. And so I don't know any technical improvement they want to do.
Okay.
For diversing the water flow and also the sediment flow.
Okay.
The problem is, and the situation is also difficult in the São Francisco, because you have the river valley is relatively narrow and is in large parts incised into the crystalline Precambrian rocks. So construction, as you are suggesting, it would be very, very expensive.
Right. Okay.
And I'm not familiar with the political issues in Brazil, but at the moment I can imagine that they will do something in that direction.
Okay.
Thanks very much. It's a great talk.
So Karl, I can't remember which speaker mentioned that instead of sand mining, remove the sand. Actually, the mining on the river basin in Brazil is also actually maybe contribute more sediment to the river. I have no idea about these two river systems. Do you know on the river basin, the mining itself,
No. There's no big mining activities.
Oh, okay. So
but in the São Francisco River, they are doing a lot of agriculture.
Oh, okay.
And especially in the regions which are relatively dry, a lot of water is used for irrigation purposes.
Yeah. Okay.
And this, of course, is also not very good.
Okay. Anybody else?
And on the other hand, let me say, another thing is especially in the São Francisco, these are in part large reservoirs, and you have a very high evaporation because it's a hot climate.
Interesting.
And so it's also a lot of water is getting lost.
That's interesting. Very okay. Anybody else? Any other question? That's good.
Can I go for another one, Paul? Sorry.
Sure. Go ahead.
Sorry, I had to ask, Karl. You also showed the plot of the dunes in the São Francisco River. Again, it's just a minor question, but I saw you looked at the geometry of those. Do you know, are most of those dunes, if you look at their lee side angle, are they relatively low angle, or do they sort of conform to more of an angle of repose type of dune?
No, so far I remember this is work we have done 10, 12 years ago, but it's normally low angle.
Okay, thank you.
Okay, so I think, Karl, after you studied the East Asia, South Asia, those large river system, and compare this small one, I think that's really make us think about something. Oh, one more question. You talk about Parnaiba Delta. There is a new tectonic tilting, eastward tilting. So do you have a rough number? How much is cost subsiding or uplifting? Any rough estimate?
This is really hard to say. It's really, but I would say roughly that we have a tilt of 5 meters during the last 500 years at maximum.
So 5 meters, that means a sink, or
a sink in the eastern part and a little bit of uplift in the western part.
Oh, that's interesting, because you show the shoreline 6,000 years ago, about 10 to 15 kilometers away. If we plus that, the tectonic tilting, let's say 6,000 years, that will make us rethink about sea level.
But the argument what also our Brazilian colleagues say, that you have not the tilting towards the sea. This is also, this is a minor effect, but more the tilting from east-west by a fault system.
Oh.
The reactivation of a very old fault system which was formed during the opening of the Atlantic.
Oh, that's okay. That's the competition. Okay, okay, that's good. That's good stimulation for us to think about that system there. That's very nice. And so I think in 2 more weeks, on end of this month, in May 28, your friend Jose, the Jose is Jose. He will give a talk. He will give a talk about São Francisco.
Again?
It's Landim.
Ladim,
Yeah.
Ladim Dominguez.
Yes, Dominguez. Landim. He will also talk a little bit about São Francisco specifically.
Now, he is a specialist for this. Much more about.
Okay, that's cool. So I think combine your talk and his talk. We will know much more about over there the system. Okay, cool. Very good. I think it's here. Ladim. Here.
Yeah. Okay.
Yeah. On May 28, we talk about São Francisco sediment delivery system. Okay. Very good. Thank you, Karl. Thank you. Oh, Yoshi. So you do want to see something before we end, Yoshi?
Yeah. May I have one question, Karl?
Sure.
Yeah, it's nice. Great talk, Karl. Thank you very much. So I have one question on the São Francisco deltas. It's a very nice beach ridge system. Is any OSL dating or age of the beach ridges from the São Francisco deltas?
Yes, they have some OSL datings. In differentiating or in determining the different ages of this beach ridge series.
So the coastal plain looks like the inside the lagoon, the barrier system, they change to the strand plain, or how do you think
the situation is a little bit complicated because there seem to be some at least moderate sea level fluctuations after the mid-Holocene high stand. In the São Francisco, there is some evidence that the mid-Holocene sea level high stand was relatively high, 3.5 meters above the sea level. And then we had at least 2 major oscillations. So sea level dropped, then around 3,000 years before present, it went up again for 1.5 meter, dropped, and then went up again for 1 meter and dropped finally to the present day position, or a little bit lower during the Little Ice Age. And so, there are also some radiocarbon dating by the initiation of soil formation.
Okay.
But I think he will tell you in more detail these things.
Okay, thank you very much.
Okay, Karl, thank you very much. Hopefully, maybe end of this year or maybe at least the next year we can meet face to face.
Would be good.
Maybe we can have a party again in Saigon. Okay. Thank you, Yoshi. Thank you, James, and thank you all the friends. So I